Starting? Yeah. Okay. All right. Good morning, ladies and gentlemen. Today we are extremely honored to have Professor Sarang Gopalakrishnan to join us in celebrating the Lunar New Year by giving us a talk about his recent research on open systems. Sarang obtained his bachelor's degree from Amherst University, Amherst College. Before he moved on to pursuing his PhD at CQIQC. Now, as a faculty member at Princeton University, his research broadly intersects with mathematical physics, quantum information, quantum dynamics, and even computer science. So on this warmest day of this Toronto winter, let's give Sarang a warm welcome.
Thanks. That's, I guess, a very interesting day to be here. Am I going to get some mooncakes at some point? Is that okay? Right. So I want to talk about some stuff that I've been thinking about with Kurt and Tibor, who have kind of different attitudes towards it. I guess you can see their faces. Yeah, it's sort of beginning of some project of trying to make sense of what the phases of open quantum systems are. When I talk about steady state phases, I'm going to talk about something fairly specific. So I'm going to think about a system coupled to a large environment. And I'm mostly going to treat the environment as Markovian for the things I'm going to talk about today. But of course, that's an additional assumption that you can imagine relaxing. So systems out of equilibrium because, for example, it's coupled to two baths at different temperatures, or because it's being driven by a classical field. And if you keep the system finite and you take the bath to infinity and you take time to infinity, eventually the system's going to come to some steady state, maybe a limit cycle, but like some kind of steady distribution. So what I want to talk about is the sense in which these steady states can fall into distinct phases, the way equilibrium states fall into distinct phases. So that's going to involve a set of limits, which I'm just going to specify right now. It's just like some choice. It's not necessarily the only choice, but it's a reasonable one. The bath, of course, you want to be functioning as a bath, so you want it to be much bigger than the system. So take the bath to infinity first. Then you take the system size to infinity, and you let the time the system is evolving go to infinity as well. And I'm going to assume that that's done in a way that sort of the time is blowing up as some large polynomial of system size as you take both to infinity. But that's a bit negotiable. And so we know that if you take the thermodynamic limit on an equilibrium system, it forms it goes into some equilibrium state. These equilibrium states form phases. So properties remain kind of the same inside a phase, and they change abruptly when you hit a phase transition. That's the boundary of the phase. Right. And so why am I thinking about this? Are there non-trivial phases? We know there are because effectively people constructed a bunch of examples in the 70s and 80s of steady states that provably form, the provably robust to perturbations. So there are regions of parameter space where the steady state of a non-equilibrium system retains some property. Like, for example, it might have long-range order, and then when you change your parameters past a certain value, the phase goes away, the long-range order goes away, and you end up in sort of a randomly fluctuating soup of stuff. One thing that's interesting about these non-equilibrium phases is that they can have properties that equilibrium phases in the same dimension wouldn't. So, for example, there's this dynamical system called Toombs rule, and its properties. You sort of see what it consists of is a bunch of domain walls being eaten away, but in a sort of patterned top to bottom way. as you might all remember, the Ising model in 2 dimensions does order at finite temperature, but it only forms an ordered phase when the external magnetic field is 0. In Toome's rule, you have ordered states that are stable in the present. You have bistability that's robust against an external field. So it's ordered in the presence of a finite field. And so it's clear that not only are there phases, but the classification of these phases is different than it would be in equilibrium in the same dimensionality. So that's some motivation for thinking about these. Now, what am I going to talk about today? So the 2 basic questions you could ask about phases of non-equilibrium systems. One of them is a really hard question, which is constructing and proving the existence of certain stable phases. So it'd be very cool if I could do that, but that's hard, and I'm not gonna address that question today. I'm gonna use results that mathematicians came up with establishing these things exist. What I'm gonna talk about today is a slightly easier question of just trying to understand what the landscape of parameter space in these open systems is like. What does it mean to be in a phase? What properties are common across a phase? What changes in a phase transition? And as you'll see, when you start thinking about this question, which might seem not terribly contentful at first, you realize there are a bunch of puzzling phenomena that occur out of equilibrium that you don't really see, that don't really have equilibrium analogs. I should say, as I'm speaking, just interrupt me if you have questions. Don't wait for the end. Right. So that's going to be the rest of this talk. So I'm going to give you a quick review of how the structure of phases at 0 temperature works, and then I'm going to talk about what changes and what stays the same when you go to open systems. Right, so a quick review of gapped phases of 0 temperature systems. So you've all probably seen phase diagrams. I guess yellow and green look the same on this screen, but that's okay. So this is supposed to be green. It's a region where there's no gap. Right, we're talking about 0 temperature stuff. So we're talking about the ground state of a Hamiltonian. And so if you like, we're talking about the properties of a Hamiltonian as well as its ground state. The Hamiltonian implies its ground state, but not necessarily the other way around. Right, so a gapped region, a gapped phase is sort of a situation where you have some number of ground states, and they're separated from the rest of the spectrum by an energy gap that remains order 1 in the thermodynamic limit, right? And so gapped phases have certain properties that are standard. So have area law entanglement. Expectation values evolve smoothly across a gapped phase. Correlation functions evolve smoothly. And then there's this interesting property that I'll revisit, which is called the principle that local perturbations perturb locally. So what that means is I take my Hamiltonian and I get to its ground state somehow. And then what I do starting from ground state is I put in a local perturbation. That's a perturbation that acts in a finite region of my space. And I ask how the expectation values far away from that finite region change in the new ground state in response to the perturbation. And the idea, again, this is totally intuitive if you've thought about this stuff, is that as you go away from the perturbing region, the effect of the perturbation decays exponentially with some characteristic correlation length that's related to the gap. Okay, so this is sort of a dictionary of this is, if you like, a list of properties of a gapped phase, and so you might say, well, what do they have to do with each other? Where does what holds this bag of properties together. And so the logic I think is like nicely formalized by Hastings and Wen in a couple of papers around 2010 is something like this. So inside a gapped phase, you can construct a path between 2 points in a gapped phase, and the path remains entirely inside the phase, right? So that's what it means to have a gap path connecting 2 points. And so if you move along a gapped path, then by the adiabatic theorem, if you do it slow enough, you're going to stay, in some sense, I'm not going to be super rigorous about, you remain close to the instantaneous ground state by the adiabatic theorem. And you don't have to do this arbitrarily slow. You can just go, if you like, much slower than the inverse of the gap. So this says that you can go from here to here in finite time. And the key point is that this thing now means by the Lieb-Robinson theorem that if you evolve the system for a finite time, then there's a light cone. So nothing changes outside the light cone. And so in particular, say the asymptotics of correlators doesn't change after a finite time evolution. And so this implies that correlation functions must remain the same asymptotically everywhere inside a gapped phase. And so the thing that holds all these properties together is this idea that any 2 points in the same points in the same gapped phase are connected by a finite time evolution to whatever approximation you care about. Or equivalently, if you try to decompose the evolution by a finite depth local unitary circuit. And so this is what it means for 2 points to be equivalent in this Hastings and Wen perspective. And so this characterization makes this list of properties that I gave you in the previous slide quite intuitive. Because effectively, for example, if you want to think about long-range order, you want to consider the correlation function of 2 points that are very far away. And so what I've drawn here is a unitary circuit that, for example, took my initial ground state to my final ground state. By assumption, I assumed there was such, by the fact that in the gap phase there is such a circuit. I can write down the circuit. And then I can say, okay, what does it do? Well, the key point is that the gates that are acting directly on the ground state don't do anything. They just leave it. They say the other way around. So I want to compute this correlation function. And so this unitary, for example, is a U dagger that crosses out against this U, right? And so all of these, everything outside the light cone just cancels out. And so if you want to compute this guy, it disconnects into 2 pieces that are 2 sort of finitely fattened local operators that are being evaluated now in the, so a single site operator at point A fattens to a finite support operator in point B if they're both in the same phase, yeah. This is a spatial correlation function, but the point is the light cone is connecting 2 points in a phase, right? So I say that, let me go back to my previous slide, if I can figure out how to do that. So I start out here. I want to argue, the thing I'm trying to argue is that the long-range properties of correlation functions at this point are the same as long-range properties at that point, okay? And so the time evolution is the adiabatic time evolution that goes from here to there. Does that make sense? So I'm saying that if I want to evaluate a single site operator, a correlation function between 2 sites in this ground state, then that's like evaluating the correlation function of fattened operator at this other point. And so this is here, and so because those two, because of the light cone, those guys just finitely fattened. I can move them arbitrarily far away, and so I don't change the asymptotics, the correlation function. Is that argument clear? You're right. Yeah, keep asking if something's unclear. Okay, so so another one of these properties of a phase is this principle that local perturbations perturb locally. So I already said what this was. So you perturb it locally at some point, and so because the key point is that locally, you sort of adiabatically turn on this perturbation if the gap remains open at all times throughout turning on the perturbation. So you turn on the perturbation, and that just corresponds to implementing a finite time evolution on the state. Now, if I apply a finite time evolution on the state, these black gates are the native Hamiltonian, that's H, and the red gates are the trotterized version of the perturbation that I'm putting in locally. Right, so the black gates hitting the ground state are just the Hamiltonian acting the ground state, so don't do anything. So I can just delete them. And so what I have after this finite time evolution is this triangular set of non-trivial. Yeah. The vertical axis is time. So so let me be very clear about this. So this is my representation of the unperturbed ground state. And so implicitly I'm thinking about it as a matrix product state in 1D, but that's not important. It's just so this tensor is the unperturbed ground state, and then I'm turning on the perturbation via this time evolution process where I adiabatically ramp it up from 0 to some final value.
Chain of flux is your entire state?
Yeah, so if you like, when I draw something that looks like, so my way of representing a quantum state of a system is something like that. So if I have 5 qubits, for example, a 5-qubit state is a block with 5 legs sticking out of it, which correspond to the states of each of the 5 qubits. So yeah, thanks. So this guy, so I wrote it out in this way with like red lines horizontally, but that's not important. The idea is this entire thing, this entire tensor is it represents the ground state of a many-spin system. And now what I'm doing is I'm time evolving the ground state. I'm time evolving it by a circuit because they've made a Trotter decomposition. And the circuit almost everywhere doesn't do much because it's the Hamiltonian acting on its own ground state. So it just annihilates the, it just goes through. It just returns the ground state. Yeah. Okay, so that's what's going on here. And so I'm emphasizing this particular feature of a of standard ground states because it's going to change when I go out of equilibrium. Okay. So that's the kind of structure that you have in Hamiltonians and their ground states. So the space of Hamiltonians splits into a bunch of these gap regions separated by phase transitions and maybe some gapless phases as well. And so we want to see, okay, what do we do? How much of this can be applied to open quantum systems? So to do that, I'm going to give you now a brief review of what open quantum systems are and what specific assumptions I'm going to make when I talk about open systems. So I'm going to think about systems in which you have a system. Your entire universe is undergoing some quantum evolution. You care about the state of some part of it. That's your system. Your system interacts with the environment, which is assumed to be prepared in some reference state, which could be either a ground state or a thermal state. It's not important. And then what you do afterwards is you trace out the environment, and that gives you an evolution on the system alone, which is defined. It's given by a super operator because what it does, it takes any density matrix to a density matrix. Right. So, but it doesn't necessarily take a pure state to pure state. It does convert pure states into mixtures. Right. And so that this object is called it's a super operator, and I'm going to call it a quantum channel, which is sort of the finite time version of it. I'm also going to use that term interchangeably with Lindbladian, which is what happens, which is basically a quantum channel that's like close to the identity from the perspective of this talk. Okay, so when you think about evaluating things in quantum channels, you'll notice that what you do is you start out with the initial state, then you apply the superoperator to the state, and then in the end you're going to measure some observable, right? And so so one way of thinking about the superoperator is sort of it takes the input state, it takes a density matrix as a vector, and converts it in density matrix to contract that density matrix in operator. Notice that observables and density matrices don't, they both look like square matrices, but they play, and they're both Hermitian, they play different roles in this evolution. This guy's the top of the circuit, this guy's the bottom of the circuit, and think about this as like this evolution operator is not Hermitian, so when it acts on the right, it does something pretty different from when it acts on the left. Its properties, its left acting and right acting properties are fundamentally different. So yeah, so these guys live in the dual space, in the space of row vectors. These guys live in the space of column vectors in this sort of d squared dimensional space. Right, and so a very important property of quantum channels is this thing called the unital property. So remember that the way I got this evolution was by taking a system, applying unitaries between the system and the environment that was prepared in a reference state, right? And so if I now instead of measuring an observable, I just measure the identity operator, which is sort of a silly thing to do, but the identity operator is a kind of it's a Hermitian operator. You can think about it as observable, and so now you look at the circuit, you see that there's nothing stopping you from multiplying the m by the m dagger and canceling them out, and then you can multiply the u dagger and cancel them out, and then what you're left with is that this entire revolution just becomes a trivial evolution. So if you like, the identity operator considered as an observable is a steady state observable, and the intuition here is just that if you don't perturb the system, it doesn't matter when you don't perturb the system. It's the same regardless when you do it. But notice that this property, which is going to be very important for us, is not true when you act to the right. So if you take a density matrix that's the identity, and you apply this entire map to it, it does not remain the identity. In fact, a simple example of a case where it doesn't is spontaneous decay. You take a maximally mixed state in a qubit, you let it evolve, it just goes to the ground state. So you don't expect these things to be, you don't expect the channel to have the unital property acting from bottom to top, but you do expect it to happen from top to bottom. And so the unital property is very important because, okay, and this is just notation for just combining all the stuff. So because when you have a channel, you have all these. So this is a very inefficient way of writing the channel, because I have an explicit representation of the environment, and then I have all this bra side stuff and all this ket side stuff. So in order to do diagrams, in order to do circuit diagrams involving channels, it's helpful to sort of fold this entire thing on itself. So the U dagger is now has been squished behind the U, and so the whole thing is just like one matrix acting on the density matrix. So now my fat input leg is a density matrix, and my fat output leg is a density matrix. This box is superoperator. And the unital property is just saying that if I contract the superoperator with the identity, interpreted as a state, then it's like not having this. So that's right. So this is a better way of saying it. So the unital property of channels is the identity that if I take the identity and I apply a channel to it from the on to the left, then it's like not doing anything. Okay, and so this seems like a rather technical point, but but the significance of it is, okay, so I don't really need to give you this example of a channel. This is, yeah, maybe I should very quickly talk about this. So the idea behind this is like a spontaneous decay channel. So you start out with some density matrix, and then what you do is you toss out the density matrix by swapping it into the environment, and you replace it with the state zero. Okay, and so this has a representation in fat line notation that you just bring in whatever, you kill it, and then you replace it with a reference state. So that's just the way this notation works. Okay, why am I telling you all this? Well, the key point is that this unital property gives me something that functions as a Lieb-Robinson theorem for quantum channels. So that basically says that, for example, if I want to evaluate a correlation function between A and B, and my time evolution is given by this open system evolution, then I can write it out like this, and I can delete all of these operations of the channel, because they're all acting on the identity to the left, so I can remove them. So the fact that you know, this should remind you of the property that I specified for the property that I used to prove various things about the unitary case. But the key point is that it also applies, light cones also exist in quantum channels. Okay, this shouldn't be surprising, because if you like, a quantum channel just consists of a unitary evolution involving an auxiliary system, and the auxiliary system just doesn't carry any correlations. You're not going to beat the light cone by bringing extra stuff in that's not sort of moving over long distances. But okay, this is how it works technically. Okay, so I'm going to talk about the phases of these circuits that are made up of quantum channels, and so when I restrict to these guys, I leave out one very important class of examples of non-equilibrium phases, and those are phases that are stabilized by active quantum error correction. Why is that? Because when I perform error correction, even though the error correction operations are local, I measure all my error syndromes, and my correction operation is based on global information about the measurement data. So in some sense, even though the quantum stuff that I do is local, it's based on it. There is implicitly non-local classical communication that my computer performs in order to read out the syndromes and figure out what error correction operation to perform. And so the things I'm going to talk about don't apply to active error correction. In fact, there's no Lieb-Robinson theorem for this case. And so the question of how to think about phases of actively error corrected systems is a very wide open question. It's not even clear what it means to have phases of such systems. So I'm going to specialize to cases where this doesn't happen. I make, let's say that any measurement data that I collect is used locally. So I don't use measurement out. So when I define the channels I'm going to talk about, I don't use measurement outcomes at site 1 to decide what to do at site 25. If I did, then I'd break this entire structure. Okay. So that's what I'm gonna. So that's I guess what I'm going to talk about. So I have these channels, and I'm going to make circuits consisting of repeated application of some channel. And I can think about that instead as a repeated application of a Lindblad master equation. It's sort of from the perspective that I'm taking, it's not, the distinction is not important, though it's going to be important for some specific details that I'm not going to talk about today. Right. So these guys. So I take quantum channel, and as I showed you, it's some matrix acting. It's some superoperator acting on a density matrix, and the superoperator is going to take every density matrix eventually to whatever the leading eigenvector of this thing is. and this leading eigenvector for the channel that has eigenvalue 1, and it corresponds to steady state. Which means that if you take the steady state and you apply the channel to it, it just returns a steady state. Okay. And so a special case of these channels are classical Markov chains, which are going to give us some of the simplest examples of non-trivial phases. So you can convert any channel into a Markov chain by just appending a complete dephasing operation to it. Right. So you know so I am talking about some kind of extremal eigenvector problem in a context where there is Lieb-Robinson bound. It looks a lot like the problem of thinking about ground states of Hamiltonians in these respects. So it seems suggestive. It seems that you should have some notion, you should have some set of corresponding notions, but a few things don't seem to work. For example, Hamiltonians or unitary operations are always invertible, right? They're inverse the unitary operation. And a distributive process is not invertible. Its inverse is not physical. And so, you know, can I even think about 2 points being in the same phase as an equivalence relation? And so that's one thing that would puzzle you. Another thing that might bother you is the gap of a distributive process can be interpreted as a decay rate, right? So if I take, for example, if I take a density matrix and I look at its time evolution, it's something like I write it in terms of its eigen vectors as you know, it's lambda, so it's this is the eigen. I'm just expanding time evolution, the eigenbasis, and these guys, these eigen values are less than 1. So if I apply the channel a bunch of times, I'm gonna get exponential decay of all the things that are not the steady state, right? And so you might say, well, okay, here's a system with a gap, and so if I evolve for a time much longer than the gap, I'm gonna turn everything into the steady state. So I should not have slow relaxation. So the idea of having a non-trivial phase seems almost incompatible with the idea of having a gapped quantum channel or a gapped Lindbladian, right? Because in order to have, if I can always start with a product with a trivial density matrix, and this argument seems to suggest that if I take this trivial density matrix and I evolve it to some time much longer the gap, it's just going to turn into a steady state. But then that's saying the steady state was connected to the trivial density matrix by a finite time evolution, which would, in my way of thinking, say they're in the same phase. So you might say, well, this doesn't make any sense at all. Yeah. Yeah, that's right. So it's just repeated time steps of the map. So let me go back over here. So I've done 1.5 iterations. Like this thing is a single iteration, right? And so when I apply the map, say 10 times, that means I'm applying this block 10 times in succession to whatever my initial density matrix was. There is, but when you trotterize, the velocity is set to 1. At least in this trotterization, the velocity is set to 1. But yeah, so you want to think about the velocity as being 1 in the circuit construction. You can set it to be 5 as well, but then that means I've got to draw a lot more gates, and it's kind of painful for me. But that's all. It's not. It's just some number. Right. Okay. So okay. How do you make all this stuff fit together? And so in this next bit, I'm going to try and walk you through an example of how non-trivial phases of open systems can arise. And the example I'm going to talk about is not very quantum. In fact, it's completely classical, and it is a biased random walk. So it's a biased random walk with open boundary conditions. So so if my left hopping, so I've got a master equation, a classical master equation where my particle hops to the left at some rate and to the right at some other rate. And if the rates are different and my boundaries and my boundary conditions are open, then I always end up sticking to either the left wall or the right wall at late times, right? Because I'm sort of moving, because if I started out in the middle, I'd eventually sort of move all the way to one end. Okay, and so a fact about this problem, about this Markov chain or this Markov process, is that it's gapped. And so why is that why is that bothersome? Well, you might say, okay, look, I have a system of size L. I start the part, let's say that my left hopping wins over my right hopping. Start a particle out here. It's going to take a time of order L to move all the way over to the boundary where it's going to get stuck. Right, so relaxation time is kind of obviously going to scale with system size. But if I just write down this matrix and diagonalize it, I find that its spectrum has a gap. Okay, so what gives? It turns out that if you just write down the extreme limit where there's no left hopping at all, it's rather simple to see what's going on. So this is the Markov chain. You'll notice that all the columns add up to 1. And what the Markov chain does is it pushes everything to one end. And so if you look at this matrix, you realize immediately the thing that makes it work out to have both a long relaxation time and a gap is that the matrix is not actually diagonalizable at all. In fact, it's a matrix with a giant Jordan block. And so so this guy's a 5 by 5 matrix, but only has two eigenvectors. And one of the eigenvectors is steady state, which corresponds to particle all the way at one end, and the other eigenvector is this guy, which is going to relax after one time step to the steady state. And nothing else is an eigenvector. So this is a funny feature of these matrices. You might say, okay, this is a fine-tuned property of this limit of the problem. But what I can do is I can go away from that limit, and I remain, qualitatively with the same dynamics. And so what happens basically is that even when the matrix is diagonalizable, its eigenvectors are almost exactly parallel to each other. And so what does this signify physically? It means that if I try to write a initial state, like a particle at the wrong end, it's like you have all your eigenvectors that are pointing this way, and you're trying to write some state that's almost perpendicular to all the eigenvectors, right? It's not exactly perpendicular because there is a complete set of eigenvectors, so there is a way to write the initial state in terms of the eigenbasis. But when you try to do that, in the large system limit, you find that you need these gigantic coefficients, which actually blow up exponentially with system size. And so this makes the existence of a gap compatible with the Lieb-Robinson theorem, because what happens is that that if I write an initial state like this out in terms of the eigenbasis, what I'm going to need is I'm going to need these coefficients that are exponentially big in system size. So if I look at the time of evolution, it's e to the something times L times e to the minus something times t. And so the point at which all these coefficients for non-trivial eigenvectors become small is precisely when t is of order L. So even though there is a gap, the gap is compatible because the strongly non-diagonalizable, strongly non-Hermitian character of the matrix, it's compatible with the existence of long relaxation times. The way that people think about these matrices is in terms of an object called the pseudospectrum. So remember that the eigenvalues are the poles, that you think about them as poles that are resolved into a matrix. And so what you do is instead of requiring an exact pole, you say that you want to study regions in which the resolvent is big instead of being strictly infinite. So you take the resolvent to be large and finite, that defines some region. If you take epsilon to be not too big, then you have a big blob. And as you make epsilon finer and finer for a finite size matrix, then the pseudospectrum condenses into a set of little circles around each eigenvalue. And the key point is that there's now a pair of limits that don't commute with each other. There's a limit where you take epsilon, the pseudospectrum, to 0, and there's the thermodynamic limit. And if you keep system size finite and take epsilon to 0, of course, you're going to end up with a complete set of eigenvalues, and the pseudospectrum is going to condense into a bunch of points. But the key point is that if you take the opposite order of limits, you never form a discrete set of eigenvalues. Instead, the pseudospectrum sort of occupies the entire block from it occupies the entire spectral bandwidth. So what happens is that there's a strict sense in which these matrices become non-diagonalizable in the thermodynamic limit, and that's precisely the sense in which the pseudospectrum doesn't become a spectrum if you take the thermodynamic limit first. Okay, so you might think Jordan block structure is a curiosity, it's a fine-tuned thing, but in fact, Jordan block structure is an emergent feature of a bunch of non-trivial phases of open systems. Yeah. 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 So what do I mean by non-trivial phase? I mean, in the language of my initial definitions, someplace, some steady state now, that it's impossible to get to from a trivial steady state, which I'm going to take to be the identity density matrix in a finite time. I'm not actually. I'm going about it. I'm going about it the other way around. So if you think about the Hastings-Wren concept of ground state phases, they're not defined, if you like, by the fundamental definition is not in terms of like some concrete order parameter. The fundamental definition is a non-trivial ground state is one that cannot be reached from a trivial ground state by a finite depth circuit. And so I'm defining open system phases in the same basic way, somewhere that I cannot go from a trivial point in a finite time. And so long range order automatically implies that you cannot go in finite time because you have to build up the long range correlations. But of course, there are many types of like strange topological order where you're in a non-trivial phase, but you don't necessarily have an order parameter that's conventional. You define order. I'm not saying anything yet about quantum, but yeah, you define what it means for an open system to be in some sense in a non-trivial phase. And then ordered phases are going to be a subset of non-trivial phases. Yeah, exactly. In the equilibrium case, I think what ends up happening is that you define quantum order in this way that's like expansive enough that eventually you encompass everything. But in the out of equilibrium setting, the notion of a non-trivial phase comes first, and then you have to say, well, what is the parameter? What is the thing that is the characterizing feature of the non-trivial phase? And that's going to be, there's no classification of that yet. But I'm right now just defining what it means to even have a classification. Yeah, exactly. Under condition that you have a steady state. You have a steady state. We're talking about a Lindbladian in terms of its steady state. We're going to specialize the case where there is a gap in the spectrum, and we're going to ask about the phases of those guys. Okay. So that's the structure here. Yeah. Everything is limited by locality. and everything is limited by having to be time independent, because I'm talking about yeah. So each block just repeats over and over and over again, because that, you know, I'm talking about phases of a Lindbladian channel, right? So that means that whatever the time evolution operator is for one like finite amount of time, that just repeats. It excludes non-locality. It excludes time dependence beyond like locate time dependence, which I can fold into my definition in a natural way.
So like the path I turn on.
Yeah, that's not allowed. Yeah. Okay, so one interesting consequence of this nature of this non-trivial you know, okay, so I don't really argue for this being a phase, right? It's just like this is just a situation where you get a right, you get a non-trivial phase, you get a non-trivial state. Why am I calling it non-trivial? Because it's qualitatively totally different from the uniform distribution over all states. And so in some sense, it's in that sense, at least, it's non-trivial. But I haven't told you about stability. And in fact, if you think about completely general perturbations, it's easy to see that this guy is not stable, because if I include some arbitrarily weak hopping between the left end and the right end, then that's going to break this entire structure, because now you're going to now you'll find that the new steady state is actually just essentially uniform. So if I allow completely general perturbations, then it is not going to be the case that these states are stable. But if I forbid this because of locality, then adding perturbations, like for example a bit of right hopping or whatever, is not going to change the nature of the state, and so it is under that restriction in effect. Okay. Okay. So this is a simple example of the kind of thing that I'm going to talk about, but of course, the single particle example that I just chose because it was easy to work through. One thing that you realize when you start thinking about these problems is, in fact, there's a very large family of problems that look a lot like this simple particle on a line example, but they now act on many body state spaces. And in fact, all deterministic cellular automata have this property that that their eigenvalues are either magnitude 1 or magnitude 0. And so if a cellular automaton has a unique steady state, then it sort of automatically has to have this property, and it takes a long time to get there, then it automatically has to have this property of having large Jordan blocks in a configuration space. And so this is the sort of very general property of open systems that's true in most cases that we looked at. And so, you know, I gave you this example of the instability to adding hopping that goes the wrong way. And so in that example, it was clear what I had to do to forbid it. But the conjecture you might have generalizing this to to general configuration spaces is basically that even though there are these Jordan blocks and they give rise to long times, local perturbations don't move you non-locally in the Jordan blocks. They only sort of move you around. So if you have a big Jordan block, it's like a staircase, and so you're up here in the steady state, and if you move all the way down there, then that destabilizes you. But local perturbation is not allowed to do that. They only move you around locally in this on the staircase. That'd be the conjecture for the structure of these objects. Okay. So I think I have successfully managed to eat up almost all of my time. So and that's good. I won't go much longer. So that's all. That's in fact most of the part of the talk that's designed to be at all comprehensible. So it's probably a good time to sort of zip through what remains. So yeah, so the basic principle that you draw from the lesson you draw from this simple example is that you know you need a gap, and the gap by dimensional analysis is some time scale. And so we've already said the gap doesn't control the relaxation of arbitrary initial states. And so what does it actually do? And so the main insight into all this stuff is that even though general initial states don't relax on a time scale that's set by the gap, local perturbations to the steady state relax on a time scale that's set by the gap. And so when you get that, then you're inside a phase. Different points inside the same phase are connected by local perturbations, and so they relax fast to each other. So you can use the channel to move efficiently between points in the same phase, but when you try to cross a phase boundary, then the channel becomes very inefficient at moving you into steady state. So that's the sort of summary of where we ended up. And so I'll just briefly present this rather formal definition of how this works. So the idea is that you say that you have a channel over here, and then so you say that any steady state inside this ball around this initial channel can be reached from it by a quick evolution. Not, you know, so this is just a relation among steady states. It's not a relation among general states. And so you have to assume this is uniform across these across the ball, and then you just sort of tile the entire phase with these little balls, and you sort of move from one to the other. You move from any point to the other by going down a sequence of these overlapping blobs. Okay. And so long story short, yeah, so one more thing I should say about this, which is you might say, well, you know, what does it mean to say that that there's an equivalence relation of phases in open systems? Of course, if I take my arbitrarily complicated state and I just depolarize everything, then I can do that in a finite amount of time with a finite depth channel, right? So what does it mean to think about being in a phase equivalence relation at all? It seems like it's a hierarchical relation. It turns out that if you define phases in this local way, then actually being in a phase is an equivalence relation. And basically the point is that if you imagine taking a highly ordered state and then letting it and then adding, let's say, a depolarizing channel, you have to do it continuously. You can't just put it in all at once. And when there's a very weak depolarizing channel, then that corresponds to a very long time to depolarize. And so there is a diverging time scale, even if you go in the direction that you might think is not an equivalence. Okay, so let me just zip through the stuff. So you can, long story short, you can prove all the same things as you would prove in the equilibrium case. Once you use this definition that I presented very briefly in the previous slide. And so the one thing that we aren't able to get a really good theoretical handle on is the spectral gap. So unfortunately, we don't really have good techniques to talk about the gaps of general many-body matrices. For that, so the conjecture that we have is that the spectral gap is the time it takes for 2 points in the same phase to relax to each other, 2 nearby points in the same phase to relax to each other. And to check that, we have to resort to numerics. So you know, the point of the slide is that it checks out and it seems to work. It's the two things track each other extremely well throughout the phase. Okay, so I had a comment about quantum order, but it's too much to talk about now. So yeah, so this is criterion we came up with. Is it actually ever satisfied? We checked explicitly that it was satisfied for some non-trivial cellular automata which have bistability. So in some sense, they really are non-trivial because they have order or conventional set. Right, and so let me stop because I've run over. The basic point of this talk was to sort of set up the question of what one would be doing if one were to classify phases of open systems, and to present some notion of like what such a classification would look like with a couple of concrete examples. But yeah, I mean, a lot remains to be done, including a proper understanding of the space of quantum orders in open systems. And a very important thing that remains to be figured out is how active error correction works inside this framework. Like, how do you define phases of systems in a way that allows, say, the toric code below threshold to be a phase? And we don't really have a lot to say there because techniques we've been using seem to fall apart because no Lieb-Robinson error. All right, thanks for your attention.